Moving into problem 3.2, this is called moving, texting, and measuring. So in this problem, we're going to continue building on our understanding with equations that we started in 3.1, specifically looking at a certain type, a certain format that occurs very often in math. So there are many relationships between variables that you can write as algebraic equations, and one simple type is what we see here. So in this example, comparing the cost of admissions to the number of students. We saw this in 3.1 with Wild World, comparing $21 to the number of people attending, we could get our cost. Another example here is finding the tax rate. So if there's a 6% tax rate on the price, what would the tax be? And then the final example here with average speed, if we know that the speed is 20 miles per hour, and we can figure out for any amounts of time what the distance would be. So if we notice, all three of these equations are set up in the same way. And that relationship in general is called y equals mx. So for example, in the c equals 21 times n, c is in the y spot, 21 is in the m spot, and n is in the x spot. Same thing here with the sales tax, the t is in the y spot, our decimal is in the m spot, and then the p is in the x spot. And lastly, with this one, d is in the y spot, 20 is in the m spot, and t is in the x spot. So if we notice for all three of these examples up above, in the m spot is our number or our coefficient. Our coefficient can also be what we consider our rate of change or our unit rate, how much it's increasing by every single time. So if we have a coefficient or rate of change or a unit rate that's all increasing by the same amount of time, our graph is going to look a certain way. If we think back to the problem with Rocky and Adrian with the bikes, Adrian's bike was $30 every single time. And when we looked at that graph, it formed a straight line because it was increasing by the same amount every single time. So when we have an equation that's written in this same setup, it's going to form a linear relationship. So all of these are going to create a graph that has a straight line. So as you begin working through here, you're going to be first starting with this table in part A, and then creating your equation from there, and then ultimately looking at graphs. So I'm going to help get you started here with the red part of the table and the equation, and then I'm going to let you work. So in part A, it says, when the bike tour is over, the riders will put their bikes in gear into vans and head back to Atlantic City. So complete the rate table to show how distance depends on time for different average speeds. So looking here in the red column, we're trying to solve for the distance when the speed is 50 miles per hour. So at 0 hours, they wouldn't have traveled anywhere that our distance would be 0. Traveling at 50 miles per hour after 1 hour, they've traveled 50 miles. After 2 hours, they've traveled 100 miles. Notice that the relationship between our time and our distance is that we're multiplying by 50. So we're going to continue that pattern for the last 2 hours. So at 3 hours times 50, they would have traveled 150 miles. At 4 hours, they would have traveled 200. We can also notice that each time we could be adding by 50 miles. That's another pattern shown here. However, we want to focus on relating the distance and the speed. So in part 2 is when you're creating an equation to compare the distance and the time. So let's do part A in creating our equation for the red part of the table we just did. So the first question we have to ask ourselves is, which one were we solving for? This time we were solving for our distance. And how did we calculate our distance? We took our time times 50, or 50t. That for any amount of time, we could calculate our distance. Remember, you can write multiplication like this, where you've got your coefficient or our rate of change right in front of our variable, just like the ones we see up above here. In part 2 with your equations, the other thing that you need to do is identify which one is your independent and dependent. So our distance is our dependent, that's what we're solving for, and what changes as a result of the time. If we know our time first, we can figure out our distance. So this is where I'm going to stop, and you should use this as a model to help you fill in the green part and the equation and the blue part and the equation. From here, you're going to use all the information from the table to then work on the next page with the graphs. So today, just keep going, get as far as you get, and then on Wednesday, you can continue working on this since you will have map testing tomorrow and no class.